Pascal. We use for the third run the same starting conditions, which is commercial wax. And we obtain something very comparable to what you can get from the literature. You have for the same inlet gas phase velocity, the increasing of the CO conversion with the increasing of the inlet H2 or CO molar ratio. This is some indication about the selectivity for methane, and if we represent the paraffin selectivity by Anderson-Schulz slurry representation, this is the alpha octane. So we obtain here for the pseudo steady state something very comparable to the literature. About the transient behavior, this is our evolution of CO conversion with the time. You can here see that to reach the steady state for some condition, we need to let the reaction about more than 25 days. And you see you can see an initial decrease for each condition. For this one, you can see you are reaching a pseudo-steady state for a CO conversion very higher comparing to the other condition. This decrease depends on the ratio inlet H2 over CO, and it's not reported here, but the methane selectivity generally follows the same tendency, which is a diminution with the CO conversion during this transient evolution. So we can think that this transient evolution is due only to the mixing of the reactor, since we are using a continuous stirred tank reactor. For the residence time for the gas, for example, inside the reactor is about 10 minutes, very lower comparing to this is the mean residence time for the liquid. Of course, for very heavier hydrocarbons, it's very longer. But if you are doing some simulation with a common expression for the kinetic, for Fischer-Tropsch kinetic with cobalt catalyst, you can expect that you reach steady state after 1 to 4 days. So what we have here is it can be explained only by the transient of the reactor. So we try to explore some explanations to explain the decrease of the initial CO conversion. The first thing we think that since in fact the rate of disappearance of CO is depending on the evolution of the composition inside the reactor, finally the initial decrease of the CO conversion would be an indication of a change of the reaction rate due to the change of solubility of hydrogen or CO, which are the reactant of this reaction. In fact, when you are looking here in this picture, where you have the molar fluxes of paraffins depending on the carbon number, you can see we are progressively replace the initial wax by the Fischer-Tropsch products. And what is going on here, you have finally a final wax lighter than the initial wax, because there is the displacement translation here of the mean carbon number of the wax. If you do the thermodynamical calculation and you approach the solubility of hydrogen, CO, and water by Henry constant, you can see the evolution of the Henry constant is very slight. There is a maximum variation below 10%, which cannot explain the initial decrease in CO conversion. Another possibility is to form some carbon deposits, and from the literature, it seems that the produced olefins may be the precursor of these carbon deposits. But in our conditions, you have here the olefins versus paraffins ratio, function of the carbon number for our free conditions. And you can see you are product the highest olefin production is observed for the lowest ratio H2 over CO, where you have the no deactivation, no initial decrease of CO conversion. So this assumption can't explain the initial decrease in CO conversion. We can suggest that there is sintering of the metal particles, but when you are finally perform two run with the same ratio H2 over CO with two different initial conditions, starting from here the initial wax A670, and here starting from another run. Finally, you get something very close for the CO conversion, and this fact indicates that you have here, if you can obtain the same conversion here and here, approximately, you can't explain the decrease of initial CO conversion by the sintering of the metal particles, especially if you assume that it's depending of the, for example, the water partial pressure. So there is another possibility, is the water cells produced by the reactive reaction. And in fact, in our experiments, we have a range of CO conversion between 20 and 90%, which is corresponding to, inside the reactor, for the gas phase, a ratio of the partial pressure between 0.1 to 1. But if you are doing the computation for the liquid concentration, in fact, due to the higher solubility from the model we take, you have finally a ratio larger, coming from 1 to 10. You have here an example for the run 3, where we have the maximum decrease of initial CO conversion. And you can see here that the water is one of the main species inside the liquid phase in the reactor. So we have here a high concentration of water, even for moderate moderate CO conversion, during the Fischer process in the slurry system. It's known that the water has an effect of the Fischer-Tropsch synthesis. This effect is depending on the support and the catalytic phase. Some authors reported that you can have reversible or irreversible inhibition of the CO activity conversion for cobalt over alumina catalyst. So initial production of water may be the cause of the deactivation of the cobalt over alumina during the reaction startup in the slurry reactor. If you are doing some thermodynamical calculation, in fact, you can't oxidize the metallic particles for the bulk metallic cobalt, but some people have done some computation and show that it's possible for small cobalt nanoparticles, and the size is depending of the partial pressure of water. So we try to modelize this initial behavior, like deactivation, where the active sites in Fischer-Tropsch are supposed to be composed of metallic atoms, which can be reoxidized by decomposition of water. We assume that this mechanism is independent and very slow compared to the FT reaction, and this mechanism is supposed to be reversible. So this is finally a very simplified mechanism with one pseudo-elementary step, and assuming that the total amount of sites is constant. This is the result of our modelization for the run with H2 over CO equal to 2.1. We obtain this calculated evolution of the rate of disappearance of CO from the mass balance of the active sites taken from the model presented in the last slide. In fact, this quantity is a fraction of sites available for the Fischer-Tropsch reaction, and is incorporated in the equation of the reaction rate and this function, finally, the deactivation function. This is the results obtained for the parameter adjustment, where you have the value here. And in fact, it's going, the modelization is satisfactory for this run, but if you are doing this for the run where we have the maximum initial deactivation, in fact, it's not correct. It's not satisfactory, this kind of approach. So, as suggested in the literature, in fact, for higher water concentration, you may have some different mechanisms. For example, you can have a formation of cobalt aluminate, which can be represented by this oxidation of the active site of Fischer-Tropsch by decomposition of water. To summarize what we presented here, in our experimental conditions, the Syngas composition has an influence of the initial behavior for a commercial cobalt or alumina catalyst in the slurry reactor. This self-produced water seems to be a key parameter responsible of this initial decrease, since you have a very important water concentration even at low CO conversion due to the higher solubility of the water. And this initial decrease is probably due to the oxidation of the metal particles by water. And we try to represent this deactivation by a simple reversible kinetic model for moderate water levels, which is giving some results satisfactory. But this approach seems to be not appropriate for higher water concentration. We would like to thank Air Liquide for their financial support, and thank you for your attention.
If you say that the oxidation is the cause for the deactivation, did you try reducing the catalyst and then doing a second run and see?
We will try to test this effectively. This model predicts that you could, if you have the good condition, reduce in situ finally the oxidized particles. But we didn't have time enough to try to do this.
The influence of water. There are various results in the literature. For instance, there's a result that the activity does not decline, that the activity increases when there's some water in it, and when the methane selectivity is reduced. So it's a complicated situation. The particle size is important, the very small particles, the oxidation depending on the particle of the water and so on. Obviously one has to control all these things and measure what happens to really understand this.
Yeah, right. It would be a good start to try to measure in situ the size, the distribution of the size of the cobalt particles, to have to see if we can go deeper in the modelization.
And then it appears that the surface of the cobalt is depending. The surface is roughened, yeah, under conditions by the CO also corrosive absorption is. So you have a different surface then that depends on the conditions and the initial time, and so this again has to be taken into account, and so stability, regeneration, and so on. So these are nice results, but to make general conclusions appear to be difficult.
Yeah, right. You're right. It's very, very complex. Thank you.
Other further comments? Okay. Then I think we are more or less almost in time to conclude our session. Some last
Thank you.